the determinant of A minus lambda I equals 0 is called what? The characteristic equation. And lambda is an eigenvalue if and only if the determinant of A minus lambda I equals 0. We talked about the definition of an eigenvalue and an eigenvector, and you sort of had to be given one to find the other. But today we're going to learn how to find eigenvalues without first being given an eigenvector. So the key is that the definition of an eigenvalue eigenvector was that AX equals lambda X, right? That's the definition of eigenvector eigenvalue. Lambda is the eigenvalue, X is the eigenvector. So when you solve this, like if you were going to try to solve this equation, you would solve AX minus lambda X equals 0, factor out an X, and you get A minus lambda I X equals 0. So this is the equation you're trying to solve, right? But in order for this equation to have a non-trivial solution, right, A minus lambda I is just a matrix. And we studied in the invertible matrix theorem, in order for this to have a solution, X, an eigenvector X, that's not 0, because the definition of eigenvector excludes the 0 vector. That's never an eigenvector. So in order for this to have a solution that's not just the 0 vector, the matrix A minus lambda I has to be singular, right? Not invertible. So then we can use that piece of information. If that matrix has to be not invertible, that means its determinant has to be 0 because of the invertible matrix theorem. So that's what we exploit to find eigenvalues lambda. We know that the determinant of A minus lambda I has to be 0 in order for that to have a solution that's not 0. So the characteristic polynomial is the determinant of A minus lambda I. So it's just a very subtle difference. The characteristic polynomial is just the determinant of A minus lambda I. The characteristic equation is when you set the polynomial equal to 0. It's just a subtle vocab difference. So the determinant of A minus lambda I, that's going to be the determinant. So A is -1, 4, 1, 2. Lambda times I, which is 1, 0, 0, 1 in this case. Okay, so I have, if you distribute your lambda to every entry of the I matrix, and then subtract component-wise, you're going to have -1 minus lambda, 4, 1, and 2 minus lambda. And then remember, the determinant of a 2 by 2 matrix is just AD minus BC. So this is going to be -1 minus lambda times 2 minus lambda minus 4 times 1. So you could leave it like that, but typically you write polynomials like in multiplied out form. So I'm just going to multiply and combine like terms here. And so I have -2 plus lambda. All right, so I'm going to have lambda squared. And 2 plus lambda minus 2 lambda. Nope, plus 2 lambda is 3 lambda. Lambda minus 2 lambda is minus lambda. And then I have -2 minus 4 is -6. That is what's known as the characteristic polynomial. Polynomial with lambdas in it. For a 2 by 2 matrix, it'll always be quadratic. 3 by 3, it's going to be higher degree. And then to find the eigenvalues of the matrix A, you just set the characteristic polynomial equal to 0 and solve it, and you'll have your eigenvalues. So this factors to lambda minus 3 times lambda plus 2 each factor equal to 0. So you get lambda is 3 and -2. You get 2 lambda values, 2 eigenvalues for this matrix.